So, hello dear students, welcome back to the series of lecture series on major theory with course code MMTC 202. So in this lecture, we'll see that the limit of squeakiness of measurable functions is a measurable function. As you all know that this is not true for the squeakiness of continuous function. That is the limit of squeakiness of continuous functions need not be continuous. So let us state this theorem. Let's state this theorem where let fn the statement of theorem is let fn be a sequence of measurable functions such that fn converges to f almost everywhere. Then f is a measurable function. So it's proof of the theorem. So as soon as fn converges to f almost everywhere, therefore we define a set where this convergence happens. So let's take this set. Take A equal to the set of the points in the set X such that fn x converges to fx. So since convergence is almost everywhere, so therefore measure of A complement is equal to 0. So this implies A complement is a measurable set, and hence A is a measurable set, because we know that the set is measurable if and only if its complement is measurable, and hence A is measurable. Now to prove our theorem completely, to prove our theorem completely, we first prove the following. We first prove the following equality. So to prove our theorem, we need to prove the following equality. That's this: A intersection f inverse A to infinity is equal to A intersection. Then we have union n runs from 1 to infinity, intersection I runs from n to infinity, fi inverse A plus 1 over n to infinity. So we prove this equality first. So let us choose an element in the set on the right hand side. So choose let x belongs to the set A intersection union n runs from 1 to infinity, intersection I runs from n to infinity, fi inverse A plus 1 over n to infinity. This is true if and only if x belongs to A and x belongs to this union and runs from 1 to infinity, intersection I runs from m to infinity, fi inverse a plus 1 over n to infinity. Okay, and this is true if and only if x belongs to a and x belongs to some intersection, because it is in the union of the intersection. So I can here it's n, sorry, it's n. So I can write this x belongs to some intersection. So let's take this intersection. I runs from m to infinity, fi inverse a plus 1 over m to infinity. And this is true if and only if x belongs to a and this x belongs to fi inverse a plus 1 over m to infinity for all I greater or equal to m, because it is in the intersection I runs from m to infinity. And this one, it's true if and only if this is true if and only if x belongs to a and this f of x, sorry, f of x belongs to a plus 1 over m to infinity. Okay, now since x belongs to a, this means that limit of f and x equal to fx. So that means limit of f of x is equal to ix, as this I is greater or equal to m, I is an integer greater or equal to m. So therefore we can take the limit I approaching to i's approach, we take this I approach to infinity. So but the limit of f of x, then I is approaching to infinity is f of x, as x is in a, x is in a. So therefore I can write it as this is true if and only if x belongs to a and f of x, because limit of f of x is f belongs to a plus 1 over m to infinity. And this is true if and only if x belongs to a and f of x belongs to, since f of x belongs to a plus 1 over m to infinity, therefore it's also in a to infinity, as this interval a to infinity is bigger than this interval. And its converse is true. Whenever f of x belongs to a to infinity, I can find m sufficiently large such that f of x belongs to a plus 1 over m to infinity, because I can choose that m sufficiently large so that this whenever fx is greater than a, then fx is also greater than a plus 1 over m. So the converse is also true. That's why I have written here if and only. It's true. Converse is also true. So this is true if and only if x belongs to a and x belongs to f inverse a to infinity. And that's true if and only if x belongs to a intersection f inverse a to true. So thus this proves the equality. Thus we have the following. Thus we have obtained this equality: a intersection f inverse a to infinity is equal to a intersection union n runs from 1 to infinity, intersection I runs from n to infinity, fi inverse a plus 1 over m to infinity. So this proves this equality. Now look at this. This is our function fi. It's measurable because fn is just, we can say, measurable function is, therefore inverse image of every interval is measurable. So in particular, inverse image of this interval a plus 1 over m to infinity under this fi inverse image is measurable. So this set is measurable actually, because fi is a measurable function. So this is measurable, therefore intersection, countable intersection of measurable sets is measurable. That means this intersection measurable. Why countable intersection of measurable sets is measurable? Because you know that the class or the collection of measurable functions is sigma algebra. So that means this intersection, this countable intersection is also measurable. And then I take the countable union of that countable intersection, it's again measurable, because again the class of measurable functions is and sigma algebra. So that means this is a measurable set actually. This intersection union is measurable set. A is also measurable, already discussed, and this therefore this whole set is the intersection of two measurable sets, A and this union intersection. So hence it's a measurable set. So I can say therefore A intersection F inverse A to infinity is a measurable set, is a measurable set. So also this set, also this one, A complement intersection F inverse A to infinity is measurable. Why it's measurable? Because this set is subset of this one, A complement. This intersection of A complement and F inverse A to infinity is subset of A complement, and A complement is a null set. Therefore, this set is also a null set. This intersection is a null set, and we know that every null set is a measurable set. So that means both the sets A intersection F inverse A to infinity and A complement intersection F inverse A to infinity are measurable sets. So now we need to show that this set is measurable. F inverse A to infinity is measurable. But this set, it's equal to, you can say this is equal to, X intersection F inverse A to infinity, because F inverse A to infinity is subset of X. But this X can be written as A union A complement, then this intersection F inverse A to infinity. And now let's apply the distributive law of intersection over unions. This can be written as, so this implies our this set F inverse A to infinity is equal to A intersection F inverse A to infinity, then its union with A complement intersection F inverse A to infinity. And we have already proved that these two sets, both the sets are measurable. So therefore, the set is also measurable. This implies F inverse A to infinity is a measurable set, and hence F is a measurable function, and hence F is a measurable function, and hence F is a measurable function. So that proves this theorem. The limit of a squeakiness of measurable function is a measurable function. So next we prove that the limit superior of a squeakiness of bounded measurable functions is again a bounded measurable function. So let's prove this theorem now. Let's prove this theorem. Let